welcome to session 6 in the series Analog Circuit Design using ADS, and this is Anurag Nigam. And in this session I'm going to talk about again about the devices, their small signal models and their applications, right? So we are looking at a MOSFET, so I'm going to look at a small signal model of a MOSFET. So in this series I'm going to look at a small signal model of a MOSFET. Okay, so question comes is, what is a small signal? And the answer is a signal which is small enough, which doesn't change the bias conditions. That would be called small signal. So let's quantize this for a MOSFET. So for a MOSFET, we know that IDS is equal to mu n COX by 2 W by L into VGS minus VT square. Correct? Now I introduce here a small signal which is Vi as a input. So that will result in a current. So this is a small signal input. Okay, so this small signal input will result in a current II, which will be mu n COX by 2 W by L. This is overdrive, right? So overdrive square, so plus of Vi times of overdrive square. Okay, now what I'll do is IDS plus II is equal to, I will take V overdrive common, right? So I will take V overdrive common, mu n COX by 2 W by L V overdrive square 1 plus Vi divided by V overdrive whole square. Now I'm going to expand this term on the right hand side, so it will be 1 plus twice of Vi over V overdrive plus Vi over V overdrive square. So that will be the term which I will substitute over here. So if I do that, I am left with IDS plus II is equal to mu n COX by 2 W by L V overdrive square is common, so this is there, plus I will have this term common, mu n COX by 2 W by L V overdrive square times of this number, in which I'm going to again borrow out twice of Vi over V overdrive. So that will leave behind 1 plus Vi over twice of V overdrive. Right. Now this term and this term are the same, so I'm left with II is equal to, this term would be, okay, so this will be GM 0 times of Vi times of 1 plus Vi divided by twice of V overdrive. Now VII divided by Vi is GM small signal, should be equal to GM0 provided Vi is much smaller than twice of V overdrive. Okay, so over here we have proven, okay, that as long as input voltage is less than twice the overdrive voltage of the device, the signal can be regarded as a small signal. Now once we have cleared what is a small signal, let's look at a model. Okay, a small signal model for a MOSFET. So I'm going to look at a small signal model. Okay, so what happens is there are two regions of operation which are of interest. One is the triode region. Okay, in this region, okay, output resistance is going to be small, right? So, and we can say it is more or less linear, right? Okay, so what I can say is, let me just draw what it will look like. Okay, so what's going to happen in the triode region is, I have got the gate oxide, so this will be gate. Then I have got the drain, and I have got the source, right? Source and drain. And what's happening is, this is going to be a channel, right? So, but the channel, okay, so let's say I go from linear region, okay, so as I keep on increasing VGS, okay, its VGS is greater than VT, so in that condition the channel has appeared. Now I have applied VDS, and that VDS has resulted in a pentagonal nature of the channel, but the channel exists between source and drain, so channel is connected to both source and drain. So the input capacitance CGS would be equal to COX WL, that's the total area of gate, divided by 2, and then CGD will also be half, that's there. Okay, so now that is there, CGS and CGD. Now when it comes to output resistance, right, that's going to be close to linear, because if you remember, I had written an equation, IDS is equal to mu n COX W by L times of by 2 times of twice of V over drive VDS, right, minus VDS square. Now what I'm going to do is, I'm going to assume VDS square is very small, so then I am left with, okay, VDS over IDS is equal to, VDS over IDS is equal to 1 over mu n COX W by L times of V over drive. Okay, so roughly this is going to be your output resistance RDS. Okay, so this is out of the picture. Now if I assume other effects, like the source is not at the same ground, DC ground, as the small signal, right? The DC ground is, well, DC voltage is much higher than the ground, or 0 volts, then there will be body effects and all that. So I'm not going to talk about body effects here. Let's look at the saturation region, where I will talk about body effects. Okay, so let's talk about saturation region. So in saturation region, VGS is greater than VT by V over drive. And second thing what we have is that VDS is greater than VGS minus VT or V over drive. So that will called a saturation region. Now in this region, the model would look like this. There would be a CGS, there would be a CGD, and there would be a GM here, and there will be one GMB, which I'm going to talk to you in a bit. GMB, which is a GM due to body effect. Then there is going to be output resistance RDS, and then there is going to be a capacitance CSB. So this is body terminal, this is source terminal, this is gate terminal, and this is drain terminal. Sorry, this is the drain terminal. And so there will be a capacitance between drain to body, CDB. This will be the high frequency model. Sorry, this will be the high frequency model for a so this will be the high frequency model for a MOSFET. So this will be called CSB. Okay, now I'm going to talk about what is body effect. Okay, if you look at threshold Vt, Vt is equal to Vt0 plus twice of Q epsilon Na divided by Cox times of root of twice of phi 0 plus Vsb minus root of twice of phi 0. So that's what our derivation was. Now if Vsb equal to 0, then this term Vt0 is equal to Vt, and this additional term won't be there, right? But if Vsb is not equal to 0, it's greater than 0, then this term would cause the Vt or threshold voltage of the device to go up. Now the scaling factor here is this. This is the scaling factor. Now if you assume thin gate oxide, then COX is going to be large. So when COX is large, so this term is going to become very small, right? So the body effect is more observable when the gate oxides are thick. When gate oxides are thin, then you will not see a lot of change in Vt, right? Similarly, if the channel is doped lightly, right, then you are not going to see the effect, the body effect a lot, right? If the channel is doped heavily, then you would, right? So this is one of the effects. So let's write down, okay, body effect. Okay, so first thing in a body effect is Vt is greater than Vt0. Now it all depends on the doping in the channel and the oxide thickness. Okay, second effect which is going to happen is the following. Okay, there is this IDS, and this IDS becomes a function of VSB. Then this will be called GMB. Okay, so now we will see this, that there would be a additional transconductance introduced which will be opposing GM, right? It will be in opposite direction. So we will see that. Okay, so that's additional body effect. So now let's see what are the various components in a small signal model. One is GM, which is called transconductance. Okay, and its unit is going to be ampere per volt, right? So this is very simple here. So okay, what's going to happen is GM is going to be equal to dou IDS by dou VGS. Am I right? Let me see if I'm recording. Yeah, it is under recording. Fine. Okay, so in this case, let's just consider IDS is mu n COX by 2 W by L, W by L into V overdrive square, or VGS minus VT square. So that twice of VGS minus VT will come in, right? And then again dou VGS. Okay, so with respect to VGS, right? So this would become equal to mu n COX W by L V overdrive, which is same as twice of IDS over V overdrive. So we are done with the GM, or transconductance. Next is transconductance due to body effect, GMB. Okay, that is going to be transconductance due to body effect. Again, the units are going to be ampere per volt, nothing special in it, right? Only thing that is going to be in opposite direction. And how do I know it will be in opposite direction? Let's see. Dou IDS by dou VSB is what we are looking for. That will be GMB. So if I do that, I would have mu n COX by 2 W by L, and then it is VGS minus VT square, so it will be twice of VGS minus VT, and now I will have to introduce dou VT by dou VSB, and there will be a minus sign here because of differentiation. So this would be minus, and this thing is same as GM, right? And let's see what is dou Vt by dou Vsp, right? So let's look at dou Vt by dou Vsv. Okay, so that you have to consider Vt0. Vt0 will vanish because it's not a function of Vsp. Then you have this term, twice of q epsilon Na over Cox. Okay, so just 1 second. Okay, by Cox times of square root of this thing, right? So that will become 1 over twice of square root of twice of phi0 plus Vsv, correct? And then yeah, so I can assume this to be gamma, this constant to be gamma, this constant. Then I'm left with twice of root of twice of phi0 plus Vsp. Okay, so this will become GMB is equal to dou Vt by dou Vsv will be gamma divided by twice of root of twice of psi0 plus Vsp. Now, this is a negative sign with respect to GM, right? So GMB is in the opposite direction. So that's what GMB is, right? Now, this is there, and then the next term is output resistance RDS. Okay, RDS is the output, is the output resistance. Okay, so RDS is the output resistance, and what that is, I have already put it down earlier. RDS is equal to 2 over lambda. If you want, you can derive it. You have to just do IDS, dou IDS divided by dou VDS. Now in this VDS you have to consider the what you call channel length modulation, right? So in this case it will be okay, mu n Cox by 2 W by L VGS minus VT over, that will be overdrive square times of 1 plus lambda times of VDS minus V overdrive. Now in this case lambda is a function of VDS and this term is a function of VDS, so you have to do you know, differentiation by parts. So it will be lambda, so this differential will be lambda dou this by this plus, right, plus this term VDS minus V overdrive times of dou lambda by dou VDS. Okay, so this would be the differentiation for this term, and if you simplify you will come to this term as 1 over phi 0 by VDS minus V overdrive plus phi 0. So that's what you will come to. Okay, so this will be the resistance which we have earlier discussed also, so I'm not going to spend a lot of time on this. Now let's go to CGD, which is also called the Miller capacitance, and this CGD is responsible for the gain roll off, the first corner frequency. Okay, so let's see what that thing is going to be. So I'm going to talk about CGD. Okay, CGD is going to be gate to drain capacitance. Gate to drain capacitance. Okay, so CGD is going to be gate to drain capacitance. Okay, now to find CGD, what I'll do, I should know what the device looks like, right? So a device has this gate oxide, and there is going to be source and there is going to be drain, and this is P minus, and this is going to be the gate, this is source, and this is drain. Now what has happened is the channel is found, but it is pinched off now. So that way source and gate, source plus gate, they are connected together, while the drain is pinched off, right? So that capacitance cannot be done half and half between CGD and CGS, right? So we have to find out the right formula. Now what happens is, in a process there is a certain there is a certain overlap here, or rather you can say that these n plus junctions, okay, they go much inside than what physically they should be, right? So in that case there is a small gap which is called overlap. Okay, so the overall capacitance CGD will be because of this fringing here. So there will be fringing fields like this, right? And this would cause the capacitance CGD to be equal to WL overlap, right, times of COX. So that will be the CGD. Now comes to CGS, which is the gate to source capacitance. So CGS will be gate to source capacitance, right? Okay, gate to source capacitance. Now okay, now to find out CGS, what I'm going to do, okay, there would be a component which is going to be because of overlap, which will be very small, but besides that there would be it. So let me just draw this over here. Okay, so let me just draw this over here. And then you have got the gate oxide, and then you have this, which is n plus, this is n plus, and this, if you remember, is the length, correct? This is the length, and then the voltage is basically dropping. So if I take the voltage across the channel, it's going to be dropping till the pinch off is hit, right? So till we hit the pinch off, the voltage is going to drop like this, right? So at pinch off, this voltage would be, so I'm considering a pinch off case, right? At pinch off, the net voltage across the channel would be 0, right? And this length would be L, so it is 0 here. So this distance is basically Y. Okay, so any point the voltage is going to be VGS minus VT minus V of Y. Okay, so if this is going to be the voltage, then the charge QY is a function of Y would be equal to COX times of VGS minus VT minus of VY, right? Now I also have a relationship, right? So if I want to find out the total charge would be integral 0 to L of, okay, okay, Q of Y dot dy, and same thing I'm going to do on the left hand side, 0 to L COX times of VGS minus VT minus of VY times of dy. Now I want, instead of dy, so I want to substitute y integration to VDS, or in this case the limiting case would be from 0 to VGS minus VT, where the pinch off takes place. Okay, so the limits will change. So let's say this results, left hand side will result in total charge Q, and it will be negative charge, so I have to drop the sign, so we'll do it later, divided by, if I do VGS minus VT, so that will give me CGS. Okay, so for now let us consider Q is equal to, and I'm going to substitute Y from a relationship. So let's check that relationship somewhere when I was deriving the current. Okay, so let's just go back a little, and here somewhere we were deriving the drain current. So the drain current, I had this equation here, so I will copy this equation, right, and then I'll paste that equation over there. Okay, so I'm going to paste that equation over here. Okay, so let me just get rid of that. Okay, so this is the relationship. So I can replace dy with something which is divided by id, right? So if I substitute this over there, I would have an integration from 0 to VGS minus VT. Okay, and then I would have mu n COX square W. Okay, so I forgot a W here, sorry. So there will be a W here. So W square times of VGS minus VT minus VY square times of dVy. Now we are in the right integral. Now this whole thing is divided by ID. Okay, so now I have to integrate this term and apply the limits. So its integral is going to be minus, and that minus minus will cancel, so it will become plus mu n COX square W square by ID times of VGS minus VT minus VY raised to 3 now divided by 3, and then I will apply the limit 0 to VGS minus VT. Now this will result, the first term will result in 0. The second term will result in mu n COX square W square by ID times of VGS minus VT cube divided by 3. Right? So this should be equal to the total charge. So this will be a minus term. This will be equal to the total charge Q. Right? Now mod of Q would be dropping the sign. So divided by VGS minus VT will be equal to CGS, which will be equal to mu n COX by 2 W by L VGS minus VT square, and the remaining terms is going to be, I divided by L, so I'll multiply by L. I divided by L, so I'll multiply by L. Then I have divided by 2, I'll multiply by 2. Then I have COX square, so I will be left with COX and I'll be left with W. Now this term divided by ID. So this 3 also I can take on separately. So in this case it will become 2 by 3 here. 2 by, sorry. Okay, so this will become 2 by 3. So this term is same as this term. So I'm left with CGS is equal to 2 by 3 WLCOX. So this is my CGS. So with this I have find out the small signal components. Now there are 2 more capacitances left, which are because of PN junction, right? So one component is CSB. This will be source to body capacitance. Okay, so this source to body capacitance, okay, is going to be given by, so in this case CGS, I'll add one more, sorry, before I leave. It will be WL overlap COX. So this will be CGS. Now source to body capacitance, because of the PN junction, right? So it can be written as the junction capacitance of the PN junction. So I can write here CSB is equal to CSB0, okay, and this is area wise, divided by root of 1 plus phi 0 by VSB times of the area, which is AJS plus WL, because the channel is connected to the source, plus there will be a fringing capacitance CB0P, and this will be again same 1 plus phi 0 by VSB times of PJS, which is the periphery of the periphery or the wall which is common to the, so this is the wall which is common, this wall is common to the source and the gate. So that fringing capacitance comes to here, periphery which is common to source and the gate. Now same thing can be done for a CDB. CDB is drain to body capacitance, drain to body capacitance. Okay, so that's brain to body capacitance. Okay, so CdB is of similar nature. dB0 area wise, root of 1 plus phi 0 by V. dB will be same as VDS roughly, times of AJD. Then the channel is pinched off, so we don't have the other term. Then we have CdB0 periphery wise, and you have the same phi 0 by VDS times of PJD. Okay, where this is the wall which is common with the gate and the drain. So this covers the small signal model for a MOSFET, right? So now in our analysis we have to not include all the device capacitances, right? So for example, if I was to do just a gain analysis, right? So let's look at where is the small signal model. We just finished, yeah, this one. So let me just copy this. Okay, copy this, and then I am going to paste it over here. This is the final thing. So over here I am going to say that's pasted. Okay, so I have found out everything almost, right? Everything is covered: CDB, RDS, GMB, GM, CSP, CGD, CGS. Now what will happen is the following. For small signal analysis, and especially when the device sits in the well, so when the device sits in the well, CSP can be regarded 0, and if it is a small signal, then CDB will be also open, right? And then CGD can be also open, and CGS can also be open. So I would be left with GMB will be 0, so all I'm left with will be this and a resistance this, which I can say GDS, which is 1 over RDS, and GM. So I'm just left with this, and this will be connected to ground, for example, in case it is a common source, and I'll come to that, gate and drain. So you see that the device model is very simplified for a small signal low frequency analysis. So we will do a low frequency analysis, and then we'll look at the high frequency analysis. So I'm going to stop here for now, and then I will go to session 6 and I'll talk about the gain stages. Okay.